All right, so let's start. A couple words about myself. Good morning, everyone. This is Nicola Casari from ToffeeX. I have a PhD in mechanical engineer from the University of Ferrara in the context of fluid machinery and especially high compressible flows through machineries, gas turbines. The topic of today's speech is quite different, actually, and it deals with advanced heatsink design by using ToffeeX. So without further words, let's start with today's agenda. So we will take on this topic, going through a very brief introduction. Then we will shortly discuss about thermal management for electronics, the state of the art, and how heatsinks are actually useful and are used for heat dissipation. We will then switch to a few words about topology optimization, how we can leverage this new tool to obtain very efficient and very effective heatsinks. We will have a short demo on how to set up a program with ToffeeX, so how to properly set up by using our software, how to obtain a solution and heatsinks for a specific application. And this will be followed by a question and answer session. So if you have questions, please do keep them for the end, then we will enable the discussion. And if the time permits, we will have a little bit of discussions about this. All right, few words about the importance of thermal engineers in the field of the electronic industry and especially electronic device. Well, our role in this industry is basically to accommodate and to permit to having electronic devices to be smaller and more powerful. Of course, having this high heat density is an issue for the thermal management, because these guys tend to become very, very heat, very, very warm, and therefore we need to design heat sinks and to design structures to mitigate the temperature in these components. All this science goes through the name of thermal management, and thermal management is necessary in order to keep the temperature of our electronic devices in the optimal operating range, which is different for each devices, and therefore each of them might need a unique heatsink or unit device which is able to reduce its temperature. By ensuring proper operating temperature range, we are able to ensure proper operating temperature, and we are able also to ensure good performances. It is very important for us to ensure this, and the common state is to use in the current state of the art different operating systems. So we have heat dissipation, which is based on air cooling, heat dissipation, which is based on liquid cooling, and heat dissipation based on phase changes. So the most traditional way is air cooling. It covers the vast majority of the part of heated devices, of heatsinks which are out there. Typically, we divide them in active and passive heatsinks. Active heatsinks are when fans are used to blow air through our component, and passive heatsinks are when the only driving force for the heat management is just the temperature difference between the device and the outer environment. Liquid cooling is where we have a liquid to remove heat. So when there is a coolant going inside our components, or being very, very close to the component to mitigate the temperature. And also an increasing trend for miniaturized electronics is to use heat pipes. Heat pipes enabled by using a refrigerant to mitigate the temperature, and basically we exploit the phenomenon of phase change in order to extract a lot of it in a very short, in a very small space. Within the context of this webinar and this presentation, we will focus only on heat sinks, and specifically we will have a look at passive heat sinks. As I already mentioned, the primary objective of an heat sink is to dissipate heat. And in order to carry out this task properly, heat sinks tend to have a very large surface area, need to have good thermal conductivity, need to have a very effective thermal interface, and need to have adequate or a good airflow, which is used for the proper cooling. So all these features are required, and thermal engineers are quite used to design heat sinks having these capabilities. In order to pick and to design a proper heat sinks, we typically rely on what is commonly known as electrical analogy, which is a simple and straightforward schematic which can help us in understanding the requirements of our heat sink. I think most of you will be familiar with this. We have that we tend to make a parallel between our thermal circuit and an electrical circuit. If you remember, the electrical circuits are typically studied by using the Ohm law, in which the electrical resistance is equal to the voltage divided by the current intensity. We can make a parallel here in what is called the thermal analogy, where the voltage is replaced by the temperature difference. The intensity current is replaced by the heat power, and the thermal resistance is therefore the equivalent of the electrical resistance. This approach is very convenient because it helps us to quickly schematize, to have a quick view of the overall system, which needs to dissipate heat from the heat source towards the external environment. And therefore, we have that the resistances of the, for example, of the junction, of the case, and of our heat sinks simply add in series, and therefore the total resistance of our heat sink and of the total resistance of the entire assembly is basically the sum of these three components. In a more the essence of the thermal resistance is basically the capability of the material to conduct heat. So by having a closer look at this formulation, basically the resistance of the sink actually is equal to the temperature, the maximum temperature of the sink, which typically occurs on the bottom surface where it is attached to the casing via the thermal interface, minus the ambient temperature divided by the heat it needs to dissipate. So basically, in other words, the thermal resistor indicates how many degrees in temperature will rise, the heat sink will rise for each watt of dissipated heat, more or less. So the objective of the heat sink design, and specifically in our case of the optimization, will be to minimize the thermal resistance of the heat sink in order to keep our electronic device, which is below our heat sink, as much cool as possible. Out there is a number. There is a real number of heat sinks, and they differ in terms of material, in terms of manufacturing, and in terms of shape. So we typically have copper or aluminum. They are the most spread material there. They can be arranged in different type of shapes. And they can also be very different one another. The most by far the most common heatsink is extruded aluminum, and this is very good, but it has, of course, some limitation. We can go to skived heatsinks in case we need further better performances, or even CNC machined heatsinks are often used. However, these devices are typically might vary a lot in terms of cost, performance, and also directionality of their performance. So, for example, we see a number of elements here. All these elements, however, are known. Let's say that all these shapes and all this configuration are known since several years, and they are kind of standard references. By what we want to present to you here today, and some hints we want to give you, is that if we need to design a brand new heatsink, what engineers typically do is to stick to experience and to stick to what they have already done in the past. So this is, of course, good because we tend to have, let's say, we tend to trust what has been done in the past. It has always worked. Why shouldn't it work again? However, there are a number of solutions which hasn't been explored yet, and therefore it might be useful to have a broad view to this problem, as there are many variables that actually can enter this equation. And in this specific context, what we would like to introduce is what is called fluid topology optimization. What is fluid topology optimization? Well, it is a mathematical approach which finds the best solution, the best distribution of material within a defined space. Well, in other words, we might have a volume. We might think of our problem as a volume, labeled by omega in this slide, in which a certain set of variables exist. So we have the state x, which in a physical problem are represented by the pressure, the velocity, and the temperature. And therefore, the problem is how to distribute material inside this volume in order to optimize the heat transfer, and in order to maximize the thermal dissipation in proximity of our heatsink. By using the fluid topology optimization, what we do is we solve we have an objective function identified by f, which is indeed function of the state variable x, but also of a new variable which is alpha, which is the impermeability. Basically, what we do is to distribute material, let's say randomly, inside this space, and we assess the performance of the distributed material in terms of how much it can be dissipated. How can we do this? Of course, the material distribution is not actually random, but the solution of a fluid flow problem in which this material distributed represents the walls is subject to certain constraints, and these constraints are the governing law of a flow motion. So we have the conservation of the mass conservation, we have the momentum conservation. These are the first two laws, and we have and we also, of course, we transport temperature, and so we have the conservation of the energy as well. The topology optimization is what is at the base of Toffee, which is the software Toffee AM develops. Toffee is a physics-based, it's a physics-driven engineering design software. What does it mean? It means that we solve a topology optimization problem based on based on a CFD solution. Therefore, this approach allows engineers to create products which maximize performance, ensuring the physical soundness of the solution, as we always solve an optimization which goes hand in hand with the CFD solution. So basically, the basis of our technology is a CFD simulation. A few examples of what we can do is reported in this slide, and you can see how different heatsinks can be generated. So we can have active or passive heatsinks. On the left-hand side, for example, you see how a passive heatsink can be generated, and this is just it gives you the idea of having a coral. And eventually, most of the times, the solution our software obtains is very organic, and it resembles you of something which is bio-inspired. But it's not an input we give, it's because nature understands what's better, and our software is actually being physically driven, really try to mimic this approach. On the right-hand side, on the other end, we have an heatsink that has been optimized using always by Toffee, but using by imposing an airflow going from the top to the bottom. So it is a forced heatsink. It's an active problem. We mentioned that there are many manufacturing techniques in the field of heat exchangers, but not only in this field. Actually, typically what our platform offers is the ability of choosing the manufacturing process you would like to use for your specific heatsink in order to constrain somehow your solution to be produced by that technology. So, for example, you can see here the solution, two different solutions to the same problem. You can have a more traditional manufacturing. If you have a closer look at the bottom, at the top, at the central image, sorry, you can see that this solution is two-dimensional, but extruded, and therefore it can be realized, for example, by milling. Whereas on the bottom, you can see a full three-dimensional shape, and this must be done for sure by additive manufacturing. But also we offer a number of manufacturing, what we call manufacturing constraints, which is actually to keep into account the manufacturing technique within the optimization process. An example of the optimization and the optimal level you can reach by using Toffee is provided in the slide. On the bottom, you can see a more conventional shape. It's a pin heat exchanger. It's quite largely used in the industrial context for natural convection. An analysis of this specific geometry provides a thermal resistance of 1.5 Kelvin per watt, and this translates in a maximum heatsink temperature of 340 Kelvin. By uploading the same design domain and uploading the same boundary condition and applying the same boundary condition to our problem, you can easily see that Toffee is able to create shapes which looks like natural or naturally oriented, and by using this organic shape, you're able to achieve thermal resistance of 0.9 Kelvin per watt, so much better. And this translates in a much lower temperature, maximum temperature of your heatsink, and therefore this translates in a lower temperature of your electronic device which is beneath it. An example of active heatsink, which has been done in collaboration with Rico, which we thank for the possibility of showing you, is reported in this slide. Rico has this conventional design heatsink, which was done by using aluminum extrusion, and they wanted to optimize the design, and by using Toffee and coupled with their aluminum binder jetting printer, they were able to obtain a much better design, which translates in an improved performance of about 15%. A very brief overview on how to set up this problem in our platform. So you can see here more or less of our platform, how our platform looks like. But bear with us, and we will have a very quick demonstration on how to set up a passive heatsink in a few minutes. So if you would like to have an active heatsink optimization here, you can just upload the design domain to our platform, which is all the available space your optimization can go into. You just pick a few. You just select a few options. For example, you go for a fully three-dimensional optimization here. Optimization type to minimize the pressure losses and maximize the gain. And you just need to give an objective weight, neat objective weight type, and neat objective multiplier. Reason for this is the fact that you are optimizing for two objectives which are competitor. Minimize pressure losses would ask for an empty channel here. Maximize the gain would ask for a very densely populated channel here. Therefore, you need to specify whether to push towards a more heat transfer oriented solution or towards a more pressure loss oriented solution. You pick once this is done, you should choose the material, and then you go to the boundary surfaces, in which you need to specify the boundary conditions. If you remember, a few minutes ago, I mentioned the fact that our software is physics-based, therefore it solves CFD simulation, and therefore you need to specify the typical parameters which are needed for a fluid dynamic simulation. As you might see, our software is very simple, so very few inputs to be done. In this case, you want a surface normal velocity of 3 meters per second, because this was the boundary condition there. You just pick with your cursor the surface you want to push to choose as an inlet. Same thing for the outlet. And after a very short period of time, you will be able to download the geometry as provided. So this will be you have the possibility of downloading the STL of the geometry ready for further post-processing and manufacturing, and also the outputs. Being CFD based, you can immediately download the solution in terms of fields. So you can have the visualization of the velocity inside your component, of the temperature inside your component, and whichever quantity you might be interested in. And that's the final result. If you want, you can also perform a CFD analysis on the solution. For example, for further investigation, if you need more insight into your problem. I believe now it's time for us to have a look at how our software works, and we will try together to set up a problem in order to obtain a passive heatsink for a common solution, for a common problem. Okay, let's go to our platform. As you might see, our software is cloud-based, so you just need to enter the URL, and you are available. You land in our dashboard. There are many examples here. If you're interested in knowing more of how are our capabilities, you can just drop us an email, and we will be more than happy to guide you through all these examples. In the concept of this specific webinar, we're interested in natural convection, and we will see how to obtain a shape like the one which is reported in this preview. You can see how simple it is to carry out this optimization. So we call this test heatsink. Yeah. So not webinar. As physics, we will choose the fluid physics. We also have the structure optimization and heat conduction, but for the time being, we are only interested in the fluid physics. We create the problem, and there we are. So first thing we are asked to do is to upload design domain. So what we're going to do is to upload first an STL, which is our computational domain. It's a simple box. We will go for 3D optimization. Optimization type is going to be minimize temperature for natural convection. We have a number of optimization type. Again, drop us an email if you would like to know more of this. We can switch to the fluid properties now. Fluid properties for this specific case will be air. In the context of natural convection, our problem will be solved by using the Boussinesq approximation. So you need to enter the Boussinesq reference temperature and the Boussinesq thermal expansion coefficient. You can pick a material, we have steel, aluminum, and titanium as precompiled, but you can feed in your own material if you have a specific a material which is not in our database. Boundary surfaces. Okay, now it's time to set up the physics of our problem. So basically, what I would like to set up with you is it's a symmetrical problem. So you should imagine this box to be just 1/4 of a large domain, and this is a good idea, so we can save some computational resources, and we can still capture the physics of the problem. So we will label the minimum X surface and the minimum Y surface as symmetry. Pick the cursor, minimum X. Boundary type is symmetry, collapse. Minimum Y, symmetry too. And we obtain symmetry. And basically, that's it, because all the rest of the surfaces are considered to be at a fixed temperature of 300 Kelvin, which is the reference temperature we have used for the Boussinesq approximation the former time. That's it. We're okay with the boundary conditions. So now it's time to upload the design space within this computation domain. I'm going to specify the volume fraction at 0. We have the gravity, which goes in the -z component. I'm going to add a volume here. So this will be the optimization domain. Upload STL, design domain, open. As you see, the design domain is smaller than the computational domain. Reason for this is that we do not want our heatsink to extend too much, but still we want to give some room to our CFD solution in order to develop the vortices and to develop the physical structures that arise due to temperature difference. Default properties, this will pick the properties we have chosen earlier. We're not going to set an heat source here yet, but we're going to specify the volume fraction. This is not compulsory. You can leave the volume fraction. You can have a higher concentration of materials. So volume fraction of 1 means this guy is fully solid. Concentration of 0 means it's fully fluid. So you can specify the amount of you want, or you can also not specify it. For this specific application, I like to have a certain volume fraction. That's it. we add a new volume, which is the heat source. We can either specify the coordinate, but I'd like to upload the STL because this guy is again symmetrical. So you see that we are actually just considering 1/4 of the entire problem. Default material, this will be solid because this is the actual source of heat in our domain. And we're asking for minimizing temperature. Again, there is a weight to be supplied here, but we leave it as the default for the time being. Now switch to the mesh tab. All right, again, it's a CFD problem, so we might want to start with the to specify the mesh size. If for this specific case is 0.25 millimeters, and we do not need to do much more here. So switch to the solver setup. Maximum number of iterations for our topology optimization would be something like 1500 should be enough. If you remember, I mentioned that the fluid topology optimization is based on the distribution of solidity inside our domain. And this solidity as in order to reflect into an obstacle to the flow is always linked to an impermeability. So how impermeable is it to the flow? We can either go for automatic or we can go for manual. So for example, these numbers are typically, the default number are typically quite good. We might just increase it a bit in order to be sure to have more solid material, in order the solid to be more solid, but it's fine. And that's pretty much all. All right, we would like to increase a little bit the number of sub-iteration mode. These sub-iterations is related to the fact that our topology optimization is based on a joint approach. So it means that we solve an adjoint system of equation alongside the fluid system of the classical governing equations. Therefore, we need to iterate among them. And we found that for tightly coupled problem as natural convection, and with tightly coupled, I mean that the temperature solution actually affects the pressure and the velocity because they are linked with the Boussinesq approach. We need to iterate more and more between the two systems in order to achieve better convergence. Typically for pressure loss, for only pressure losses or for incompressible problem, just leave to one is enough. A better convergence is required if we need to switch to an higher number of, if we switch to this kind of problems in which the variables are tightly coupled. Okay, we're done. Basically, what we want to do is to pick the number of cores. This depends on the licensing system you have access to. 8 CPUs are enough for this. And we also might want to see the results, intermediate results, so the solution update. All right, we can launch the job now. And after this problem, it really depends on the number of elements or the number of cores you have in mind. Being a CFD-based solution, the problem scales more or less as CFD. Thing is, you might need to wait for 4 to 5 hours to solve problem as complex as natural convection. We are typically much faster, so our solution tends to be in the order of minutes. So you could have a reasonable solution in 1 hour, for example, if you have a a common heat transfer problem without accounting for natural convection. But as natural convection is a tightly coupled problem, it typically tends to take more time for convergence. However, we can fast forward here, can load this job, and we can have a look at the results. So basically, this is exactly what we have done together, but after a few hours, we can hide the volumes we have used, as well as the design domain, and the solidity, which is generated by the topology optimize. The optimization is available for you to download, and you can have a look for example, at the fluid domain as well, which is what is not solid, of course. We could download the STL, we could download the outputs, and we can also add a validation, which is a full CFD simulation of our problem. All right. Having said so, I believe this leads us to the end of our presentation, and we thank you for your attention. And if you have any questions, please feel free of asking them now. Thank you very much.